Gotcha.
Yeah, I'm not lecturing, but I'm happy to take any questions that you have about anything. And then
Okay.
next week, TA office hours will be happening, and I'll be holding office hours as well. And then Tuesday's lab is going to be dedicated to this homework, and Thursday's lab is going to be dedicated to homework too. But I'll post an announcement about that as well. You guys are on top of things. Last year, I didn't have anybody in my first office hours. So yeah, I'm happy to start taking questions whenever.
Oh yeah, go ahead, Lola.
No, go ahead.
Yeah, so just for doing like exponential family, like showing that different distributions are exponential family in general, like we just learned a different format, I guess, in theory, which is just this like h of x, c of theta, and then exponential with your natural parameter and like t of x, I think. Do those, I guess, do any of, if you're familiar with that, do any of those correspond to like the scale parameter or like a convex function?
So you're talking about the Casella-Berger definition of the family, I think.
Yes.
And so somebody asked this question last year and I looked into it. I don't remember off the top of my head exactly how those two link, but I can talk about it a little bit on Tuesday because I have some notes on it. But I would recommend putting it in the form that I talk about in the slides, which I can write down here actually. I can share my screen in a second, just because it sort of is the way the people who sort of invented the GLMs originally wrote it this way, because it's sort of everything naturally it's easier to sort of find all of the different components that I'm talking about.
Yeah, I would guess if I took some time, they're equivalent.
Yeah, they are. And I have some notes on that actually, but I just don't remember off the top of my head the equivalence between the two forms. And like sort of, I know there's a reason too why Casella-Berger did it one way and the original GLM people did it the other way. I just don't remember. Hold on. I'm looking for my lab from last year actually, because I kind of did some stuff on that. But I'm happy to take other questions in the meantime.
What did you say? You're taking more questions?
Yeah, so I think that Casella and Berger, yeah, so the notes basically say that the original form for the GLMs comes from this paper by McCullough and Nelder, who invented the GLM, and the form that they provide, which is what I have in my notes, is designed to be like nice specifically for linear models when you have covariates, which we'll get into next week. And it's easy to find the link functions that sort of fit well with your data and put it on a good scale. And it's also easy to find the expectation and the variance that way. But Casella and Berger uses the other notation because it's easier for finding sufficient statistics, which come up a lot in theory.
Gotcha.
But I don't really talk about so much in my class.
Okay, good to know. Thank you.
So my question is, can you go over this canonical link function? I guess I don't really understand this whole thing, please.
Yeah, sure. So I'm going to talk a little bit more about that in lab on Tuesday as well. But essentially, so I'm going to just share an iPad to the screen so I can write on it. Okay. And okay, sorry, it's taking a little bit for the iPad to get connected so I can start writing on it. Can you see? There's always going to be some technological kinks to get worked out the first time. Okay, here we go. Yeah, so the exponential family form that we're going to be working with, I'm just writing down right here. And so when you put your distributions into the exponential family form, you'll be able to have, you'll be able to sort of show like what T of Y is, what B of theta is, what theta is in terms of the parameters from whatever distribution you're working with. And I think in the lecture notes, I go through the normal distribution. And I show that in that case, your T of Y is equal to Y. And your theta is equal to mu. And your B of theta is 1/2 mu squared. If your distribution is in canonical form, which is just sort of a definition of the exponential family form, you're going to have T of Y equals to Y like you do with the normal distribution. And if it's in canonical form, then the canonical link function is going to be whatever function you have here for theta. So here, in this case, you have theta equals mu. That's called the identity link, meaning that you have the, you're not sort of doing anything with mu. And I know that that's probably not a particularly satisfying definition, but I can show you another example. If you go through the one with the binomial distribution in the lecture notes, you end up with theta equals log pi over 1 minus pi. Now you have a different function of the original parameter in the distribution is this pi, or sometimes you see p for the binomial distribution. And so your canonical link is just this function of pi that gives you theta. So in this case, that would be like log of x over 1 minus x would be the function. Oops. Hold on, I'm trying to erase that. I know that might not be a particularly satisfying answer. Bear with me, I have to relearn how to use this thing. There we go. And the canonical link comes in when you start talking about GLMs, which is in the week 2 videos, where you want to be able to connect whatever distribution you're using with your covariates and the parameters from sort of a regression model. And I'll talk about that a little bit more on Tuesday to make it more clear. But in terms of this homework assignment, what I want you to do when you're talking about the canonical link function is that's the function that would be on the right-hand side of the equation here. That is a function of the parameters from your original distribution that gives you the theta on the left-hand side of the equation. Does that make sense?
So does that mean, so it's whatever theta is equal to? Is that what it is?
Yeah, it's it's the function on the right-hand side of the equation. Yeah, that gives you theta. So in this case, it's like log of pi over 1 minus pi. So this is called the logit function, log of some random variable, say x over 1 minus x is called the logit function. Sometimes you see that written as logit of x. And so that would be the canonical link function for the binomial distribution.
So does it have to always be log of something?
Not necessarily. That's something that depends on what distribution you're using. So what I just, so for the normal distribution, it's not the log of anything. It's just it's called the identity. So just, you don't have to do anything to the random variable to get the canonical link. It's called the identity link, meaning just it's itself. That's what that means. So yeah, it depends on the distribution that you're using. And I'll go through a couple other examples on Tuesday.
Is the scale parameter the same thing as A of B?
Yes.
Okay. And I was also wondering, like in the 4th and 6th problem on the homework, I've never seen the gamma function before and I had to Google it, but I still don't really understand what it is and, you know, how to like manipulate it as a log function and everything. So
yeah,
maybe...
yeah, I can talk about that a little bit. Gamma function is one of those things I Google what the form takes like every time I look at it too. So that's fine that you don't recognize it. But essentially, all PDFs have to integrate to 1 by definition. And so some of them have sort of weird constants associated with them so that they integrate to 1. And that's what the gamma function is there for, just to make sure that it's a true PDF and it integrates to 1. In case you're curious, I actually have to look up how that's defined because I don't remember off the top of my head. But typically,
yeah, I was kind of wondering, like when you do like the exponent to the log of 1 over gamma and whatever's inside it, like what does that do? Or is it considered like a constant or?
Yeah, so typically I would just treat that as a constant function of
Okay.
constant function of alpha in this case. So I don't know if you can see my screen or if you can see the Wikipedia page I just pulled up, but yeah, it's like a weird integral.
But we don't have to actually do the integral?
You don't have to actually do the integral. So
okay.
So what I would say is if you have something like the gamma distribution and you're starting to put it in exponential family form, what I normally do is something like this. I lost my screen. Hold on. There we go. Let's see. So you have, for the gamma distribution, you have, at least the way it's written here is, And this kind of applies to the chi-square distribution too. Someone asked a question about that on the discussion board. So I'm saying here that the shape parameter alpha is known. That means that this whole thing is really just a constant. So for this problem, and then you can just treat that as a constant. So if you're starting to put this in exponential family form, you would have this is equal to something like e to the log b. Oops, my handwriting is not always excellent, and I apologize for that. Something like that. And then this term that we're discussing here, I'm just going to make that another color. Oops. Yeah. Well, I just erased it. See, there's going to be some learning curves here, but in terms of me getting used to using this thing again, sorry about that. But so essentially, you're going to have in that exponential term this like log gamma function of alpha term, and you can just treat that as a constant because we're saying that alpha is known. And if it's a constant, that means it's just going to be absorbed into that c of y and phi term.
Okay, that makes sense. I was a little confused about number 4 because we weren't treating k as a constant.
Yeah, so for that one, you're not treating k as a constant. So it's a little bit different. And like if you want to go through and derive, take the derivative of that sort of by force, you can. But I don't expect you to. There's the gamma function is sort of a common function that comes up. So there's, I think it's called the digamma function is the derivative of it. Something like that.
So like that part that was like 1 over the k over 2, 2 to the k over 2.
Yeah, I'm fine if you like sort of look that up and then sort of. Sorry, go ahead.
Yeah, I didn't know if we should be treating it as a constant or if we needed to.
Oh, so for that, you don't want to treat it as a constant. In this case,
but we can look it up, and
you can look up what the derivative of that is because you're going to need that for the v theta to get the expectation and the variance.
Okay.
So figuring out what the derivative of that gamma function is with respect to k, that's sort of the piece that you need.
Okay, perfect. Thank you.
So just to double check, so for the b of theta, like we always need to solve it, like after we find it out from the formula, we need to solve it using the theta that we found earlier, something like that.
So you want to put, I think if I understand your question correctly, yeah, you want to put b of theta in terms of theta, which I don't have that written down here. So for the normal distribution where I wrote out, and I know I'll say this again, but I'm going to sort of walk through a couple of these on Tuesday and sort of what my expectation is for how it looks for the homework too. But right now, so I have b of theta here written for the normal distribution, which is 1 over 2 times mu squared, but that's written in terms of mu, not in terms of theta. So I would want you to write that in terms of theta. And since we have that piece here, we have theta equals mu for the normal distribution, then in terms of theta, this would be 1 over 2 theta squared. So you can substitute that. So for other distributions, you won't necessarily have theta equals mu, so you would have to substitute something else. But yeah, putting b of theta in terms of theta is good. Is what I want you to do.
Julia? Julia, can you hear me?
Who's speaking?
Carol, can you hear
yeah,
me?
I can hear you. Yeah.
Okay. Are you open for another question?
Yeah, absolutely.
Oh, okay. Just a quick one on just whether or not this is legal or not. On the, like for the first problem, when you asked about the exponential function, you wind up getting your t of y theta minus b theta with opposite signs. Is it acceptable just to assign alpha of phi as -1?
Yes, definitely.
Okay. All right. That was just, I want to make sure that was okay.
If you don't do that, then you'll end up with a negative, taking a log of a negative number, which you can't do.
Okay. Thank you.
Yeah. Yeah, I'll take questions all the way up until class time is over. So
Julia, I have a question about number 4, and I know it was mentioned earlier, and probably we'll go through an example on Tuesday. But I was having trouble even starting it or getting it into exponential family form, the chi-square distribution, and I was wondering if you could help with just starting that out, because I know so there's a single parameter k, and after taking the after putting all of the terms into an exponent form, I still didn't see a way to cleanly get it into that like t of y times theta form.
yes, so I haven't done this one again lately, but we can go through it together, kind of step by step, and see.
Sure.
And you can see if I make any errors. Some of them, and I don't remember off the top of my head, like I have to sort of write up the solutions and think about it for a little bit. Some of them are exponential family distributions, but don't have this like nice canonical form. So you can still kind of, you have a function of t, like function of y, which is your t of y times some function of your parameters, which is theta, but they won't necessarily be as nice in the sense that you don't have this like t of y equals y, or you don't have like a closed form solution for your theta. That can happen with some of these distributions, and the chi-squared might be one of them.
Yeah, I mean, that would make sense to me, but I don't know if someone else found a solution, or if there's a trick involved with simplifying the terms. I'm kind of left with a bunch of log statements.
I don't remember, so let's see. I mean, that's a good exercise anyway to sort of go through it. So, accept it.
Yeah, I think I had ended up with like log y instead of y or something like that.
There we go. I'm struggling with the iPad. Yeah, so starting to write it in, I'm my hunch is that this is just not one of the ones that isn't nice. And I'll have a better explanation for you guys on Tuesday for sort of what that means in a practical sense, and the difference between the ones that have like a nicer form and the ones that don't. but I don't remember off the top of my head today, so I'll have to look into that. Yeah, but I see what you're saying, like, because you're going to end up with like a log y term instead of y. So
Yeah, yeah. I ended up with log y, and then some terms with like k over 2 in it. But yeah, it would make sense if it doesn't get into canonical form. Um, so so log y might be the t of y function. Um, and then I assume that that means something different for how we derive the expectation variance if it doesn't get into canonical form.
It does mean something different for it. And that's where I think Trent's question about the form for from Casella-Berger, I think Casella-Berger generally handles these types of distributions that don't have the nice canonical form better, because then you can use sufficient statistics. But that's like sort of a little bit of a hand-wavy answer. Yeah, I think that's what's going on here, though.
Also, like I was looking at the chapter 3 of the Dobson book for its like formula for the exponential form, which they kind of presented even another type when there's a single parameter. And I was wondering, do your equations from the slides, do they for this part come from Dobson primarily, or is it like another source we could look at for alternative forms?
Yeah, so I'm just grabbing a textbook. So the Dobson is mainly based off of this book by McCullough and Nelder, which I'll put it in the I'll put it up in the book section on the website. But this is sort of like the standard PhD level GLMs textbook. And the people who wrote this textbook also wrote the original paper on GLMs. And they come up with this sort of original form that I have written up here. And Dobson comes from this book. It's sort of at a little bit of a more applied level, but they do have like slightly different notation. It's fun and good practice when everything writes something with like slightly different notation and you have to figure it out. That's a joke. It's sometimes really annoying when that happens. But yeah, the McCullough and Nelder is like the original, and that's where a lot of this notation comes from.
And where's a good place to like get the derivative of that K thing? Like a good source to use if we're not going to do it by hand.
Let me think on that, because let me think on that and get back to you.
Okay.
I'll post something on the discussion board.
Thanks.
Same with the rest of the form for this question, right?
Yeah, that sounds good.
Any other
So
questions?
I have a question. Yes, just to double check for the negative binomial on the bottom, is it n minus 1 or is it supposed to be y? I'm
M
not
minus
sure.
one.
I'm sorry.
M minus one.
Oh, okay.
There are a couple different forms of the negative binomial distribution, different ways of like parameterizing it and writing it down. And this is just one of them.
Julie, you had mentioned that there was the book that was more applied, a little less of the big GLM book you held up. Was that the Dobson one that you have linked?
That's the Dobson one, yeah.
Yeah, great.
This is kind of a tangent or just a note like that I found in the Dobson book. In the section about exponential families, which is like 3.2, they give an equation or a form of exponential families for single parameter distributions, and that form is the same form as the Castellan-Berger, albeit just for single parameter distributions like Poisson or exponential. But for Trent's question, I think it was like a convenient way of like linking the two. And then when more parameters are involved, they kind of diverge a bit. And I'm not sure how they map together, but there's a little bit of a link there.
Nice. Okay, I'll check that out. I have that book in my office and this book in my office here. So gotta go back to my office at work and grab it. Oh.
That's in the Dobson book, Ray?
Yeah, it's Dobson, and the PDF is online. I guess the page is page 46 of the PDF.
Okay.
So there's a nice form there. The letters, like from Sam's class, like the letters of like h of x, c of theta, and all that aren't exactly the same, but the form is pretty much the same.
Gotcha.
Also, just the link for the Casella-Berger Statistical Inference Second Edition, the link is broken. 404 is out.
Okay, yeah, that's good to know. Thanks. I wonder if they took that down and it's not online anymore. I'll look into it. Okay. Sorry, my screen stopped sharing, didn't it?
I have a kind of specific question. I don't know if you can go too in depth on it because it's like about the answers to one of the questions. But I keep on getting that the expected value of y for the exponential is 1 over theta. And I'm not sure. I know that's wrong.
There are different forms of the exponential distribution. Sometimes it's parameterized the way that I have it written down there, and sometimes it's parameterized with one as like 1 over lambda times e to the negative 1 over lambda times y.
Gotcha. So in this context, that does work then.
Yeah, so if it was parameterized the other way, you would have like the inverse for the expected value that you get.
Okay.
Right here.
What would the purpose be of like parameterizing it differently?
Yeah, it's just like about what scale you want the values for that parameter to take.
Okay.
If it's going to be like, if it's like 1 over theta, then it's going to have like small values.
Right.
Yeah.
That makes sense.
Yeah. I think if you want to think of it as like a scale versus a rate, sort of.
Yeah, I think just from having a semester of theory, I keep on wanting to go back to my Casella and Berger distributions and knowledge.
Mm-hmm. Yeah, so I mean, but it's good to it's like good to sort of practice seeing it in different ways. And
yeah, definitely.
Yeah, because like most of the time too is like you can reparameterize things and it doesn't change your expected value too much. You just have to take the inverse of it.
Okay. Awesome.